Yes, Assalamualaikum. In this lecture, we are going to discuss the voltage control in a single phase inverter. Before this lecture, we have discussed introduction to the inverters, single phase inverters, and three phase inverters. Now we are going to discuss the voltage control in single phase inverters. Let's start. AC load may require a constant or variable voltage as their input terminals. Uh, Whatever you connect at the inverter terminal, you know the inverter is DC to AC converter, and load may require anything, constant voltage or the variable voltage. Okay, so your inverter methods of controlling the output are external control of the AC voltage. We just connect something here which will control the voltage or which will regulate the output voltage, or we should, if we need something over here, we just modify this DC externally without touching the inverter. And the third thing is the internal control of inverter. So we have three methods. If you need to control the voltage, output voltage depending on your load, one is just manipulate this alternating current at the output. Second thing, just manipulate the input, that is the DC to the inverter. And third thing, that is the most important in this case, is the internal control of the inverter. You just do or control some parameters of the inverter which are controlling the output voltage, or we just modify them. Okay, this is the basic theme of this lecture. Let's discuss one by one. The first two methods require additional components. Of course, when you are going to control the output by this DC, surely you need some feedback path, and for that feedback path you need a certain circuits which will compare the variation in the alternating output voltage and fed the feedback back to the DC, and it will adjust its input. The In the case when you are going to modify this one, you need to attach some regulators over here. Okay, and of course you need additional components for these first two. However, for the third method, which is the internal control of the inverter, we don't need any additional components. We will see how. So discuss one by one. The first one is external control of AC output voltage. Output voltage of inverter is controlled by using an AC voltage controller like that. Surely constant DC, you have an inverter, you have a constant AC voltage. Now you have introduced additional AC voltage controller, and which will produce a controlled AC voltage. Then it will fed to the load. This is the one solution. Output contains more harmonic when output voltage is low. Surely when you introduce this kind of circuit, your controller will introduce more harmonics at low voltage. Hence it is really used because for the low output side it's very bad. And maybe you have observed this phenomenon in the just in the case of AC controller, like when you touch the regulator of the fan. These days this is very fancy device, and when you try to control the speed of the fan and you will take it to the low side, I mean you reduce the speed of the fan. So at the low side the fan makes certain noise, and this is the proof of this thing. And there are some other things which we can do with the external control of AC output voltage. Series inverter control. Two or more inverters are connected in parallel. Okay, this is the scenario. One, two, they are connected in parallel, and they are both connected to the primary of the transformer, and which will fed to the secondary, common secondary. Okay, connected to the transformer whose secondary one they are connected in series. Okay, this is output one, this is output two, and they have some phasor sum, and frequency of the output voltage V1 and V2 must be same. You know, this is very similar to the some industrial point of view. If, for example, if some industry is generating its own load, its own generation from anything like gas turbine, and if it is coupling with the motor, then the frequency of the two voltages should be same, otherwise it cannot couple with each other on the same system. Similarly is the thing here, you need, if you want to add them up, frequency should be the same. Now the next thing is external control of DC input voltage. Previously we discussed external control of AC output voltage. Now we will go for the DC input voltage. What will happen in this case? What you are doing, constant AC voltage you are feeding to a fully controlled rectifier, and rectifier converts it into DC, and then you apply a filter, and you will have a controlled DC voltage. You mean that we are applying these two additional circuits. One is a fully controlled rectifier and filter to achieve the controlled DC voltage, and then it is fed to the inverter. Of course, this is the additional circuit, and then you have a controlled AC voltage. And there is another scenario, you have a constant AC voltage, uncontrolled rectifier. Okay, you produce certain DC, you apply a chopper. Chopper is a DC converter, and then you apply a filter. This chopper will help you to produce a controlled DC, and the rest of the circuit is same. Then you have an inverter and then control. Now in this case, two different scenarios are utilized here. We just, in the beginning, we just use the fully controlled rectifier, but here we use uncontrolled and then the chopper. Of course, this will add to the cost and complexity of the circuit. We have two, this is rectifier and the chopper and the filter. There is another solution, constant AC voltage, then you will add a AC voltage controller, and then uncontrolled rectifier. Actually, you already introduce a controller over here, and you rectify with the uncontrolled rectifier, then filter it, and then ultimately you got controlled DC voltage, and which will fed to the inverter, and ultimately you come up with the controlled AC voltage. It looks pretty interesting, but the complexity of the cycle in all above three cases is not as smooth, and it's not a pleasant thing. It's too much. So there is another option. We just fed the controlled DC voltage chopper. The use of chopper is that it will modulate step up, step down, whatever you need into a controlled form, then it will be fed to the inverter. And so we have a four scenario. All of them are, three of them starts with the AC voltage, then convert it using converter or use the controller, and then pass to the chopper. Fourth one is just you need a controller controlled DC voltage fed to the chopper, and then you have a situation where you have a controlled AC voltage. Now the most important parameter then. We have discussed the first two. External control of AC input, AC output, external control of AC input, and how you can control the internally, how you can internally control the inverter. Okay, output of the inverter is adjusted by controlling the inverter itself. Method of controlling the output is called pulse width modulation. Very hot topic for the inverters, and it is obtained by adjusting the on and off periods of the inverter components. Okay, that's a good thing. How we can do it, and what's the advantage? No additional components required in this case, and lower order harmonics can be limited along with the voltage control. Now the problem of the harmonics which will introduce in your output in the case of the previous phenomena like external control of output AC voltage is eliminated in this case, and filter requirement also you don't need usually in this case filters. Okay, let's see pulse width modulating inverters. These inverters can produce AC voltage of variable magnitude and variable frequency. That's great. We can work out both things, strength and frequency. And the quality of output can also be greatly enhanced when compared with those of the scale wave inverters. Now the quality. Here we talk about actually the shape of your. Usually our devices are designed for the sinusoidal voltages, and you know that usually if we see the output from the inverter single phase or three phase, it looks like the scale waves, which has a lot of harmonics. When you take the Fourier transform or Fourier series of these things, you have a lots of harmonics which will reduce the performance of your device. Pulse width modulation is a process of modifying the width of the pulse to obtain variation in the output voltage with reduced harmonic contents. What will happen is the process where you can get a modification in the output pulses by just modifying the certain control pulses, and which will result in a reduced harmonics. Okay, let's aim of using different PWM techniques is to generate a sinusoidal output voltage of desired fundamental frequency, and I just spoke about that in the above sentence. Why we need this? We need it because it's the basic requirements. All the systems are designed for the sinusoids. There are different types of PWM inverters: single pulse, multiple pulse, sinusoidal pulse, modified sinusoidal pulse, space vector pulse width modulation. Okay, we will see one by one. What is single pulse width modulation? In a single pulse modulation, there is only one pulse exists per half cycle. You should remember this. Only one pulse per half cycle. The width of this pulse is varied to control the inverter output. We just adjust the width of that pulse to control the output of the inverter. Look at this one. Okay, let's come back. This is our single pulse. What will happen in this case? This is the pulse to the G switch G1 and G2, S1 or S2 you can say, and whenever you have already seen the output due to this inverter. what will happen? In this case, you can see when your AR is greater than AC, means your reference point is greater than the rest of the signal, suppose your pulse, then you have a pulse. Where this is larger than this one, you have out. Similarly, when AR is less than AC, AR is less than AC, then you have pulse. And here is your output. So your output voltage, it will be produced when you have a reference signal greater than this, your DC signal. This is your DC signal is greater than the in this area your DC signal is greater than the reference signal, this pulse carrier signal. Sorry, this is the reference signal and this is the carrier signal. When your reference is greater than the carrier, it will produce output. And in the negative cycle, when your reference is less than the carrier, then it will produce output. So, frequency of the reference signal determines the frequency of the output voltage. Now, if your frequency of the reference signal, this is your reference, if you reduce the frequency like here, and it will, the same frequency will be introduced by this reference signal. And ratio of the reference to the carrier called modulation index that controls the output voltage. Of course, if you take the reference little bit above, then you have a large output, and if you take the reference below, then you have a small output. So in this way you can control the magnitude and frequency. You go up and down, frequency is also modified because this width is modified and frequency is modified. Output voltage of the inverter with single pulse modulation is given by this. You can find it any textbooks. We don't need to go into the details. Actually, it is derived from this, from here. Just take the Fourier series and for this scale shift, and only the odd components will survive for this kind of shape. And you can find it anywhere in the textbook, and the most simplest form like this, and the first component, and the more generalized one, and this will show you that how you can eliminate the harmonics. You have a certain harmonic components over here, and by adjusting the pulse width derived from this formula, you can just simply eliminate the harmonics. It's your control. Inference from the single width affected. Yeah, the third, fifth, and seventh hormone dominates when voltage is reduced. If you go to the smaller side, small voltages, then these hormones are extremely dominant. Lower voltages contain large amount of harmonics. Harmonic contents can be reduced by having many pulses in each cycle of the output, not a single pulse. But you should have many pulses. So let's discuss multiple pulse modulation. In this method, many pulses having equal weights are produced for every cycle. This is an example. Gating signals are produced by comparing reference signal with a triangular carrier wave. Okay, triangular carrier wave. This is your state shape comparator. Then the triggering pulses. Let's see. This is what we have talked about in the previous slide. So reference signal, your carrier signal, and whenever your carrier is larger than the reference, you have output. Whenever your carrier is larger than the reference, you have output, and it is mapped in the form of pulses. You can see here, and frequency of the reference signal determines the frequency of the output voltage. Yeah, surely this frequency will decide output voltage. The ratio is called modulation index, and it will control the output voltage. In this case, the output voltage can be expressed in this form, and more generalized if you open up this summation. And this is the first harmonic, and it's that. These slides are self-explanatory. You can go through extremely simple calculations. This is a maximum from the first harmonic. Now, if you have the single port modulation, the peak value of the fundamental voltage can be evaluated this one, as we seen in the previous case, and two pulse. You have a formula. You can calculate the gamma from there. Two values from here. It's multiple. What we have seen, fundamental component of output voltage is low for 2 pulse point, then it is for the same. You have seen previous slide. Yeah, 2 pulse modulation is lower as compared to the single pulse, and but lower order harmonics are eliminated and higher order harmonics are increased, but higher harmonic can be filtered easily. Yeah, that's the difference. In this case, we have a higher order harmonics. The scheme is advantage to the single pulse modulation because we want to avoid harmonics. Large number of pulses per half cycle requires which need frequent turn on and turn off the thyristor, which will add to the switching loss. That's another bad point. So we need a trade-off. And how about sinusoidal pulse modulation? In this case, in this method, several pulses per half cycle are used, as in the case of multiple, but width of each pulse is modulated proportional to the amplitude of the sine wave. That's the key point. With respect to the amplitude, the width is modulated. Gate pulses are generated by comparing sinusoidal reference signal with the triangular frequency of the reference signal decides the frequency of the output voltage. That's the previous one. And this is the modulation index. Number of pulses per cycle depends on the carrier frequency. This is the example. This is your carrier signal. This is the reference signal. Okay, what will happen as long as your carrier signal the reference signal is larger than it depends on the cross area or the cutting area and where it is greater the reference signal, based on that you have output, and these pulses have different width, and you can see that very clearly. And what is the modulation index? The difference between the peak magnitude of the modulating waveform and the carrier waveform. Modulation index control the harmonic contents in the output voltage. Okay, maximum divided by the carrier. Maximum divided by the carrier. This is your carrier. Summary: by increasing the number of pulses per half cycle, the lower order harmonics gets cancelled. Higher harmonics increased but can be filtered easily. High value of n resulted in more switching losses and leads to reduction of the efficiency of inverter. So if we are going to increase the number of pulses per half cycle, then we need to turn on and off your IGBTs, thyristors, on and off, introduce a switching loss. That's the key point. And this is all about this output voltage control of the inverter. Thank you very much.